Hello, I'm Cinthya França, and I'm going to present our work, Data Imputation IoT Gateways using Machine Learning. This research was conducted along with Rodrigo Couto and Pedro Velloso. IoT devices emerge every day. For example, we have smartphones, smartwatch, and security cameras. This device might have sensors that monitor, collect, and transmit data to the cloud to provide intelligent service to users in different scenarios, such as smart homes, factories, and hospitals. In IoT, a record contains data collected by sensors, as temperature or humidity, in a specific timestamp. However, collected data might present missing values due to various reasons, such as network problems, damaged sensors, or security attacks. Such inconsistent data introduce errors in data analysis, so to ensure high-quality services, it's imperative to identify and deal with this missing data. Missing data is a widespread problem in IoT. However, most data analysis algorithms work only with complete records, with values in all attributes. A typical approach is to eliminate incomplete records. However, this elimination may reduce the accuracy and reliability of the analysis. Besides, deleting incomplete records reduces the number of valid samples to feed data analysis algorithms. Another approach is data imputation, which is the procedure of replacing missing data with estimated values. For example, we can use the average, median, or value predicted by some other method. Several works address data imputation. They use statistical methods, optimization, and machine learning approaches. They usually focus on the forecast quality. However, they do not define where the proposed method runs or do not conceive methods to run in processing constrained IoT devices. And they usually use all available data from the dataset to predict a missing value. Traditionally, cloud servers perform the task of identifying and inputting missing data. However, some applications require quick response, so it is interesting to bring data processing and storage to the network edge, such as in IoT gateways or IoT devices. This will also help to decrease the network load. In this context, we propose a mechanism based on neural networks to input missing data in IoT gateways, analyzing the forecast quality, the impact of the execution time, and processing resources. So in this mechanism, each IoT gateway trains a neural network model using previous data received by sensors, and such a model is then used to input missing data at the IoT gateway. This figure shows our considered scenario. We can see that sensor 1 failed to send the humidity attribute at this timestamp, so the gateway receives the record and puts the missing value before forwarding to the application server. But as the gateways have processing-constrained resources, data imputation methods must be simple, light, and provide good predictions. We use a regression model based on multilayer perceptron neural network. The first model, called an N1, has as input data the measurements of the 3 hours that immediately precede the current hour. The second model, NN2, has the same input data that NN1, plus the measurement of the same hour of the previous day, assuming that it might be close to the current hour. So each attribute has its own neural network model and training dataset. In the training phase, each neural network is trained to estimate a value from the input data. In the test phase, missing data imputation occurs, respecting the record's timestamps order. To validate our model, we use the metrics R-squared and root mean squared error. We use scikit-learn to implement the neural networks, and their hyperparameters were chosen empirically. That is, we chose the hyperparameters combination that results the higher R-squared score. Both models use the same set of parameters. In this work, we employed a dataset called Monitorar. It has a historical series of Rio de Janeiro's weather data measured per hour. We chose the São Cristóvão station and the attributes atmospheric pressure, temperature, and relative humidity. This station has records with missing data and gaps between timestamps, which is consecutive hours when no data were collected. Hence, before the analysis, we pre-process the dataset by inserting empty records to fill the timestamps where no data is received. This table shows the missing data percentage of the employee dataset. We can see that the missing data is a severe problem, especially in years from 2017 to 2019. Our methodology consists of varying missing data percentage by removing valid measurements. Thus, our analysis uses only data from 2011 to 2016, since the last 3 years' percentage is already too high to let us introduce more missing data for testing. In our work, we want to verify how the missing data percentage on the dataset affects each imputation method results. We consider 5, 10, 25, and 50% of missing data. But first, we measure how much data is already missing for each attribute, and then, using an uniform distribution, we randomly select records with values to remove from the dataset. These removed records are later used to compare the original values with the estimated ones. We compare the neural network models with two baseline methods. The first one, called last value, consists of replacing the missing value with the last received value. We choose this method due to its simplicity and processing requirements, since it only needs to store one value. The other method is the average, which consists of replacing the missing value with the average of all values received for the attribute. It's a widely used method. However, in our experiments, this was the worst method, so we omit its results. We used data from 2011 to 2014 for training the neural network models and test all methods using data from years 2015 to 2016. We ran 50 samples for each missing data percentage, and the results are the average of these samples with a confidence interval of 95%. Here we show the R-squared score for atmospheric pressure, temperature, and humidity. Each figure shows the results when varying the percentage of missing data on the tested set and the training set simultaneously. The best possible R2 squared is 1, so the higher the score, the better the model fits the samples. NN1, NN2, and last value have a high R2 score for atmospheric pressure. This attribute has low variability, so repeating the last received value can represent a good prediction. However, this characteristic does not apply to the other attributes. For temperature and relative humidity, the difference between last value and the neural network is more significant than in the case of the atmospheric pressure. Also, this result shows that using the measurement of the last day does not help NN2 in the prediction. Hence, NN1 is simpler than NN2, but its performance is statistically close to NN2. Besides, we can see that the percentage of missing data has a low impact on the model's performance, since the R2 squared do not decrease as the percentage of missing data increases. We expected this behavior since the missing value events follow a uniform distribution. These figures complement the previous results, presenting the RMSE calculated for each attribute when varying missing data percentage. The best possible RMSE is 0. Therefore, the smaller the RMSE measure, the fewer errors the model has. The RMSE for the last value method is higher than NN1 and NN2 in all attributes. For NN1 and NN2, these values are close to each other for all attributes for all tested percentages. Our mechanism aims to work on gateways, which have scarce computing resources. Consequently, it's also necessary to analyze the processing requirements and memory footprint beyond the prediction quality. We measure the execution time and memory utilization in both training and test phases using a Raspberry Pi 4 Model B. In the training phase, we measure the processing time and memory that each neural network model needs to train all attributes using the training set. Here, both neural networks take less than 30 seconds to train and each less than 402,000 kilobytes of allocated memory. In the test phase, we measure the processing time and memory that each method needs to input all missing data from the test set. Note that this is a worst-case analysis, since we input all missing data at once, while in an online scenario, both execution time and memory to input one single record are much shorter. The neural networks slightly increase the execution time compared to last value, but all methods consume almost the same amount of memory. In reality, it's not possible to know a priori the missing data percentage experienced by an IoT gateway. So in this analysis, we fix the missing data percentage in the training phase and vary the missing data percentage in the test phase. Our goal is to evaluate the difference in the percentage of missing data between the training and the test sets. This figure indicates the R2 score when we train the neural networks considering 5 and 50% of missing data. The last value method does not need any training, but we show its results for comparison purposes. We can see that our models have similar R2 scores, regardless of whether the training set considers 5 or 50% of missing data. Also, their results remain high and better than the last value method for all missing data percentages. It's an interesting result since the employed neural networks provide good results even when there are only 50% of complete records available for training. Now, we show a clustering application case study using the algorithm called DBScan. It's an algorithm widely used in IoT, which clusters dataset records and detects outliers. However, it needs complete records. So our goal here is to compare how each input missing data method affects DBScan results. For this study, we used two base datasets. In the drop test dataset, we delete all records with missing values. And in the post-inf dataset, instead of removing records with missing values, we use the imputation methods presented before, resulting in three datasets: post-inf NN1, NN2, and post-inf last value. Finally, we run DBScan on all four datasets. The EPS parameter is chosen using the drop test dataset as baseline, calculating neighboring records distance, and the mean point is varied in different values. This table shows the DBScan results for all datasets when mean point is 72. It shows the total records of each dataset and the number of outliers detected. It also compares the drop test datasets with the others, showing how many outliers they have in common. It is interesting to note that posinf NN2 has the same outliers as drop test, and that posinf NN1 and posinf last value are very close. The last column shows the number of new outliers, namely records that are outliers only in the posinf dataset. Our manual analysis of these results indicates that all new outliers are records with inputted data that do not exist in the drop test dataset. So input missing data does not turn a valid record into an outlier. Now this table shows the percentage of outliers in each post-inf dataset, using different values for mean points. We can observe that the percentage of records defined as outliers by DBScan is smaller than 2.22%. The post-inf NN2 dataset presents the lowest percentage of outlier insertion. So this case study shows that the imputation methods provide accurate results without distorting DBScan's output. In this work, we addressed the problem of inputting missing data on IoT gateways using a regression model based on multi-layer perceptron. We validated our models using actual weather data from Rio de Janeiro, considering different missing data percentages. The models present a high R-squared score and a low RMSE compared to another simple method, and have a short execution time and low memory utilization. Besides that, our models perform well even when missing data percentage of the training set is fixed. We also present a case study that confirms that an application can use all sensor measurements, since it applies simple imputation methods instead of removing entire records. As future work, it would be interesting to verify if our mechanism also identifies anomalous data in the dataset. Another direction is to remove values from the dataset using different probability distributions to analyze the different failure patterns. Thank you.